So now this part that we were doing last time, I told you that whenever you have a metal ion, and what happens is that compounds, when they dissolve, they dissociate and they turn into ions. For example, copper 2 plus ions are formed, and SO4 minus 2 ions are formed, and they dissociate. And then I told you that they form complex ions, which are that the ions formed. A complex ion is something like this, that when copper has a +2 charge, it's going to it won't just be floating around in water. What will happen is that water are ligands. They're known as ligands. They're species which have lone pairs. And those lone pairs, those negatively charged lone pairs over here, they're going to be attracted to the copper 2 plus, which is the central metal cation. So whenever, whether it's NaCl or any compound, it dissolves, the metal ion dissociates, and the metal ion dissociates and starts attracting the lone pairs of water molecules, and all the water molecules that come sticking to it, +2 attracting the lone pairs. So at the end of the day, copper attracts 6 water molecules on all sides. You can think of these as X, Y, and Z axis. And from all sides, water molecules are going to get attracted to it. This is known as a complex ion. That's copper with 6 water molecules. It's got a +2 charge, and it has a blue color. Then we talked about ligand exchange. Coordination number was the number of dative bonds it usually forms. Now, ligand exchange was that if you have a copper with the water molecules sticking around it, what will happen is if you add a different ligand, like NHT also has lone pairs. What's going to happen is that the water molecules are going to get knocked out, and they would eventually be replaced by NH3 molecules. As more and more NH3 is added, there's going to be more NH3 molecules and lesser water molecules. So this is called ligand exchange. And I told you that the number of NH3 molecules that can surround the copper ions, that could vary. So this complex ion changes into another type of complex ion. So you change from copper with 6 water molecules to copper with 6 NH3s, or a combination of both of them. It could be 4 NH3s and 2 water molecules. So it could be any number of water and NH3 molecules. Now, I told you about the color of this complex. It was a deep blue solution. So this is what's going on. As the water molecules get replaced by NH3 molecules, the color of the solution turns dark blue or deep blue. Similarly, ligand exchange would happen that if you add Cl-1 ions, which also have lone pairs, like if you add concentrated HCl, then these 6 water molecules will start getting replaced by Cl-1s. And now Cl-1 is a bigger ligand. It's bigger in size based on its MR, on its AR. It's got an AR of 35. So Cl-1 is bigger in size. So the copper +2 starts getting surrounded by Cl-1s, but because they're bigger in size, you can't fit a lot of them around it. So usually it's a tetrahedral complex instead of an octahedral complex. Usually only 4 Cl-1 are able to surround it because you run out of space. Cl-1 is much bigger in size. So we discussed that, and this is the complex that's going to form CuCl4 with a charge of -2. And it's a greenish yellow solution. Why is it a charge of -2? Because it's Cu +2 with 4 Cl-1s. Similarly, if you start adding dilute NaOH, that has OH -1. So the water molecules, they get replaced by OH -1 ions. And this actually has no charge. So overall charge would be 0 because copper is +2, OH is -1, OH is -1. So the overall charge would be 0 over here. And in this case, I told you that usually it's just 2 OH ligands that are going to replace the water molecules, and it's an insoluble precipitate, a pale blue precipitate. copper hydroxide is insoluble. It doesn't dissolve. Now, I do remember, I just didn't write it down. So precipitates, remember that last time, precipitates are never considered complex ions. So you usually just call it copper hydroxide. You don't write the square brackets around it when it's a solid. So when it's a solid, you usually don't write square brackets around it. And in exactly the same way, you have to remember the colors of cobalt complexes, which are exactly identical. All you have to do is just replace the copper with the cobalt. Cobalt with 6 water molecules, that's pink in color. Cobalt with 4 water molecules and 1 OH ion, that's a green precipitate. Cobalt with NH3, that's a brown solution. Cobalt with 4 Cls, that's a blue solution. So the formulas are exactly the same. The structures are exactly the same. You have to memorize those. Copper and cobalt. Those are the two that you have to remember. I'll open a syllabus in a while. But before this, let me also explain. They might ask you about the colors of any of these, and they might ask you about the formula of the complexes. The other type of question that they're going to give you is they'll ask you about ligand exchange reactions. And most of the questions would be related to the ones that we just discussed above. So the first typical question that they usually ask is, and that question is about copper sulfate aqueous. So the question would be phrased in this way. And remember, it's all related to the above complexes that we just discussed. So the first thing is the test for copper sulfate aqueous is they're going to state that you have copper sulfate aqueous. A few drops of NaOH are added. अच्छा, इस केस में a few drops, if you remember the test for copper sulfate, you add a few drops of NaOH and you get a pale blue precipitate forms. And then what you do is when NaOH is added in excess, the precipitate remains insoluble. So when NaOH is added in excess, pale blue precipitate remains insoluble. Now, what they're going to ask you about is they're going to ask you for the whole explanation for what's happening here. So, what's happening here is the first thing you're going to talk about is that you don't have to write a word explanation for this. All you can do is you can just write equations. You can tell them that copper sulfate aqueous is basically, copper ions would be dissociated. There would be copper ions surrounded by 6 water molecules forming an octahedral complex. And the entire ion will have a charge of +2. And that's your blue solution. And when OH ions are added, or NaOH, these OH ions, they come from NaOH. So when OH ions are added, 2 of the water molecules, they get replaced by OH. And it ends up forming COH2 which is a solid precipitate, and that's your pale blue precipitate. And the 6 water molecules, they get knocked out. So this is what we also learned earlier as well. We did do this. I told you that, I mean, this was the case. Like if you have copper, aqueous, in aqueous state, it would be surrounded by 6 water molecules. It's a blue solution. And as soon as you add dilute NaOH, all that happens is that the water molecules, they get displaced by OH ions. It ends up forming copper hydroxide, which then leaves the solution, leaving the water behind because it's now a neutral molecule. It's not going to be attracted to water anymore. And a precipitate, a solid precipitate of copper hydroxide, which is a pale blue PPD, that's formed. So this is the typical question that you get, and that's the equation that you're going to write for that specific question. Okay, is this clear?
Yes, sir.
So then the next one. The next thing is there was another test for copper ions, and that is you add a few drops of NH3. And what you get is you get a pale blue precipitate again. If you remember the test with NH3, if you add excess NH3, then what happens is that the pale blue precipitate dissolves. And when it dissolves, it gives you, so when it dissolves, a pale blue precipitate dissolves, giving a deep blue solution. So that's the second question. They're going to ask you what's going on here. I mean, that's the test for copper ions. So explain what just happened here. So what just happened here is, let's focus on the first statement. You added a few drops of NH3 and a pale blue precipitate forms. So what happens here? Let's talk about that part first. What happens is that initially, this NH3 with its lone pairs, you just added a few drops. It acts as a base initially. What that means is that the few drops of NH3 that are added, instead of acting as a ligand, like previously I showed you, I told you that when you add NH3, slowly what happens is that the NH3 would knock out the water molecules and would replace some of the water molecules around the copper ions. NH3's lone pairs. So NH3's lone pairs are going to be surrounding the copper ions. But there's going to be one step before that. Before getting the deep blue solution, a pale blue precipitate forms. When you add a few drops of NH3, because the NH3 acts as a base, and instead of reacting with the metal ion, what it does is it instead reacts with water molecules because you've added too few of the NH3 molecules. And it acts as a base. It grabs one of the H+1 ions in water, forming NH4+1, and producing OH minus 1 ions. So instead, what you get is this particular ligand. OH ion initially acts as the ligand, not NH3, because you've added very few drops of NH3. So the OH ions that are produced act as ligands. So the first equation is that our copper aqueous, which is surrounded by 6 water molecules, and it has a charge of +2. The water molecules are not going to be replaced by NH3. Instead, they're going to be replaced by the OH ions that are being produced in the previous step, in the previous reaction. And when they start reacting with the OH ions, the water molecules, they get replaced by OH ions. So the copper is now surrounded by OH ions, and copper hydroxide is insoluble, so it's going to form a precipitate which is going to be pale blue, and the 6 water molecules are going to get knocked out. These are all aqueous. I mean, this is not aqueous, that's a liquid. So that's the first thing that will happen. So I'll just quickly repeat this, that initially the NH3, because you've added very few drops of NH3, the NH3s, they start reacting, the few drops of NH3s start reacting with the water molecules, forming a lot of OH ions, and these OH ions then go and they start knocking out the water molecules, and the OH ions, they replace the water molecules, forming copper hydroxide, which is a pale blue precipitate. Is this clear?
Yes, sir.
Sam, is this clear? Zoha, Nadine, is this clear?
Yes, sir.
I said then, now after that point, yes, I mean, you can write that as well. That is also acceptable, Nadine. I mean, this is, one second. So that is acceptable. And you can also write it as this. I mean, the reason this one is a better option is that copper hydroxide is going to leave the solution. So all the water molecules are going to be part of the solution. So they're going to be left in the solution. This would form a solid precipitate. So the COH2 precipitate would leave and the water molecules would just stay part of the solution. Nadine, is that point clear? Do you understand that point? I mean, even if you write this one would still be correct. So now the next part, when NH3 is added in excess, what happens then? Then it's obviously NH3 in excess. So when NH3 is added in excess, so now what's going to happen is that the blue precipitate redissolves. So you have this blue precipitate, which is Cu, OH2, and that's a solid. Now you start adding NH3. And since the NH3 is aqueous, there would be some water molecules as well. This state is going to be liquid. And this is what's going to happen, that the copper ions would now again be surrounded by NH3s, either 6 of them or 4 of them, and some water molecules, depending on how much NH3 and how much water is present. So these numbers can be different. But the total number of ligands, they got to be 6. It's either 4 and 2, or 6 NH3s and no water molecules, or 1 NH3 and 5 water molecules. The total should be 6 ligands. So that would give you your deep blue solution, and the OH ions will be replaced. So that is your aqueous, dark blue or deep blue. So that's your deep blue solution. So the copper hydroxide redissolves, the pale blue precipitate redissolves. So these are the exact equations that you have to, they're going to ask you about this. They're going to ask you what's going to happen if you add a few drops of NH3, and what will happen if you add an excess of NH3. Instead of writing any statement, you just give them equations. This is what's going to happen if that NH3 acts as a base initially, produces OH ions. Those OH ions, they form the copper hydroxide precipitate, which is a pale blue precipitate. But if you add a lot of NH3, then those NH3s are going to act as ligands. Their lone pairs will be attracted to the copper ions, and the copper ions will be surrounded by NH3s, and that would help it re-dissolve. Now, the last thing is with Cl-. Haji.
When we add like HCl, right? So basically, HCl ionizes, and we do have like the amount of H plus ions increases. Does this affect the formation of the complex ion? Can it?
The amount of H plus 1? Okay, the amount of H plus 1 is increasing. Yeah. That's the question, right?
Yeah, exactly.
But not in this case specifically. I'll just write down the reaction first. This is something. This is the third thing that they're going to ask you. That adding, so I'll just write an equation for that, adding concentrated HCl. What happens to copper 2 plus aqueous? Blue solution turns to a greenish yellow solution. So what's happening here? Adding concentrated HCl. So we'll just quote the equation that will. So you have copper with 6 water molecules, and it's got a charge of +2. And copper with 6 water molecules. I didn't write 6. So then we're going to replace it with Cl minus 1 in concentrated HCl. And you will now have 4 Cls because they're bigger in size. And they would have a charge of -2. And the 6 water molecules are going to be displaced. So this one, there would be 4 Cl ions. Balance this out. Now, this specific thing, this one is your blue solution. Everything is aqueous here, and that's your greenish yellow solution. Now, I don't think H plus 1 ions would play that big a role over here in any way. It would obviously be acidic because you're adding HCl, so there would be a lot of H plus 1 ions around. And it's concentrated HCl. So the only thing things that you might see is that the H+1 and the Cl ions getting together. Whenever you have HCl, you do get fumes of HCl. So probably apart from that, I don't think anything else would be happening. Okay, Basa, is this clear?
Yes, it's clear.
So that's about it. Those are the Ligand exchange reactions that we've already discussed, and you got to remember all of them. And the other thing that you got to remember is repeat everything. All the equations are exactly the same for cobalt. So you got to repeat this. I mean, repeat the same exact answers for cobalt. And obviously cobalt has different colors. So you need to learn how to write this in equation form as well. Let me just. So you should be able to write equations for these. And the questions would, I mean, these are officially in your syllabus, cobalt and copper and the Ligand exchange reactions. So these are the ones like what happens if you have copper aqueous, cobalt aqueous. You got this thing, that's your pink solution. You add OH ions, it forms a precipitate. You add NH3, the precipitate dissolves to, I mean, you add more of NH3, the precipitate dissolves, giving you a brown solution. You add Cl ions, you get COCl4 -2, so which is a blue solution. So you must remember the colors of these. The equations are going to be identical. The tests are going to be exactly the same. Everything is going to be exactly the same except just switch copper with cobalt. Is this clear?
Yes, sir.
Okay, everyone else, is this clear?
Yes, sir.
So just one second. That's the next thing. The new syllabus, just give me 1 second. I said, so first let me. So we did this part, explain the transition elements and the cobalt ions with water and ammonia and hydroxide and chloride. So for copper and cobalt, we're done with this part, the specific part. Define the term ligand, we did all that. Did bonds, we did that. Now we're going to talk about this thing, understand and use the terms monodentate. Okay, so we're done with the first two parts. What's monodentate? What's bidentate? C2O4, this one, amino ethane, and polydentate. So let's talk about these. So this thing, you got to remember the reactions and you got to remember the formulas and the colors of these complexes. Now, the next part is you just have to understand the term. You don't have to remember any specific ligand. I mean, you don't have to remember specific complexes. The only thing is you got to remember what's the difference between monodentate and bidentate. So, I mean, the first thing is what is dentate? Dentate is refers to teeth. And in chemistry and in ligands, it refers to lone pairs. Or just a single lone pair is, when you hear the term monodentate, that means just one lone pair. So monodentate ligands. So what's a monodentate ligand? It's a ligand with just one lone pair. Or it might have more than one lone pair, but only one of them is actually involved in dative bonding. So a ligand with one lone pair involved in forming coordinate bonds with the metal ion? So that's probably the definition of a monodentate. So the ones that we just discussed, the Cl minus one, water, OH ions. I mean, they included Cn minus one as well. Now these are all monodentate. I'll just copy paste one of the. I mean, I'll just copy paste this thing. I mean, all of these ligands that we just discussed, these are all monodentate because the ligand is just forming one dative bond. That's it. Just 1 second. Baza, did you is this your old question or is this a new question?
Old.
Achha, theek hai. You got the answer to that, right?
Is it correct?
Because remember, H+1 ions will not be attracted to copper plus 2, right?
Yes.
Because remember, ligands are species which have lone pairs that are, which is why they are attracted to metal ions. Is that point clear?
Yes.
Okay, so all of them have a lone pair. So now even Cl minus one is a monodentate ligand. Why? Because remember, Cl minus one has more than one lone pair, but all the other lone pairs would be pointing away from the metal ion, so it would only form one dative bond. That's why Cl minus one is a monodentate ligand. It's capable of only forming one dative bond. It's actually Cl minus one actually has 4 lone pairs in total because its outer shell is completely full. But the other ligands are pointing somewhere else. So with the metal ion, only one of them would actually be able to form the dative bond. Is this clear?
Yes.
So now the next, so that's monodentate. That's the one that we've already talked about. The next one is a bidentate ligand, which is kind of the same definition, except it's capable of forming 2 dative bonds. So they do sometimes ask for the explanation for this. So it's exactly, I'll just copy paste the same old definition, which is this one. And I'll just change 1 to 2. That's it. So it's basically going to be forming 2 dative bonds, a bidentate ligand. And 2 of them. So I'll 2 of them. Now I'll give you an example of a bidentate ligand, and they actually in the syllabus they talked about, I think it was 1,2-diaminoethane, which is CH2, NH2, and NH2. And there was another one which was I think C2O4 2-, which is C2O4. That's an oxalate ion, which is this one, C2O4. So these 2 specific examples. So we'll stick to these 2 specific examples, but you can extend the concept to pretty much any ligand. So here's my copper plus 2. And it's got these, it's, so you've lost the board. Just hold on 1 second. So I've got, so it's got these, I'll just quickly make this and we'll, so copper plus 2 has 6 sides. And let's talk about, now imagine the same thing, the exact same thing, surrounded by 6 water molecules. But now you've got a bidentate ligand that looks something like this. It's got a CH2, another CH2, and you've got an NH2 over here having lone pairs. So it's one molecule, but it's a big molecule. So what happens is that the N is capable of forming a dative bond from one side, and there's another completely different N which is capable of forming a dative bond from the other axis. So there would be 2 lone pairs that would be attracted. So this one is a bidentate ligand, and there are going to be 3 of them. There's going to be another one where you have, NH2, and they're going to be connected together. So it's going to be CH2. So the lone pairs of N will be attracted to the copper ions in the middle. And here's another one. So it's CH2. So that's an example of a bidentate ligand where there's one molecule that's capable of forming 2 dative bonds. Is this thing clear?
Yes, sir.
Sir, can you repeat this? Bidentate one.
I mean, bidentate is exactly the same thing. Remember, previously we had an NH3 molecule. Okay, we had separate NH3 molecules, right? If you had an NH3 molecule, we had an NH3 molecule. But they were 2 different NH3 molecules, right? You had an NH3, its lone pair getting attracted to the copper plus 2, another NH3 and its lone pairs getting attracted to the copper plus 2. Now, the only thing is, think of the 2 NH3s connected together. So that basically leads to, you can think of it as one molecule. But that one molecule is now a big molecule. There's an N lone pair that's getting attracted to copper plus 2 from one side, and there's an N lone pair which is getting attracted to the copper plus 2 from another side. But it's one molecule that's, because it's bigger in size, it's capable of forming 2 dative bonds. Is this clear?
Yes, sir.
Otherwise there is no difference. Kind of exactly the same as the NH3s that we talked about over here. The only difference is, instead of 2 separate NH3 molecules, you still have 2 separate ends, but they're kind of joined together with each other. Because 1,2-diamino ethane is a big molecule. So all you have to know is, you just have to know the concept of a bidentate ligand, which is this one. Okay, all clear?
Yes, sir.
So here, let's continue tomorrow now. Okay, everyone, take care.
Allah Hafiz.
Allah Hafiz.
Allah Hafiz, sir.
Allah Hafiz. Zaib, I'll send you the recordings as well, ठीक है?
All right, sir.